Hello everyone, welcome to Intro to CP session 4. Today we're going to talk about sorting in competitive programming. Now, here's the link to the slides. And the second link here is the link to the code templates we're going to use today. If you want to take a look at it right now, you can, but we're going to have a link up for every single example question later, so you don't have to worry about missing it. And the officers should be, they've sent both the links in the chat as well, so you can click on those. Now, what is sorting? It is very common in real world, right? We're just putting things in order, like we're, for example, in this case, we have an array 1, 5, 4, 2, 3. To sort this array, we are putting them in their original order, in their intrinsic order, and that becomes 1, 2, 3, 4, 5. Similarly, we can sort an array of characters according to their ASCII values. So they become A, B, C. But how do we sort in computer science? There are many different sorting algorithms. For example, there's bubble sort, insertion sort, merge sort, quick sort, and most importantly, Bogle sort. It's a really, really good algorithm that they don't teach you in computer science classes, but I recommend you to take a look at it later on your own time. I'm not gonna spoil anything, it's really fun. Now, here on the right side, we have an illustration of a sorting algorithm doing its work. And in most modern high-level languages, for example, C++, Python, Java, and so on and so forth, there's always a sorting function implemented already. For example, in C++, there's intro sort, which is a hybrid of quick sort, heap sort, and insertion sort. And it takes the advantage of these three and then combine them together to make a really powerful sorting algorithm. Some of them may ask, why do we want to learn this? Now, sorting is not only important in computer science. We shall see from this video I'm gonna show you guys. Computer sound. Okay.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president, and I mean, you're going through the rigors now. It's also hard to get a job at Google. We have questions, and we ask our candidates questions, and this one is from Larry Schwimmer. Okay. What? You guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay. I didn't see computer science in your background.
We've got our spies in there.
Well,
as you can see, sorting algorithm is not only important in computer science, it's also important for Obama, for politicians. If they want to become a president, they better know their sorting algorithms. So here's the code to sort in C++. At the top, you need to include algorithm, which is a library that contains a bunch of really powerful algorithms already implemented. Or you could also include the bits/standard C++.h, which includes the algorithm library. So yeah. And then to use a sorting algorithm, first of all, you have to have a sortable object. For example, in this case, we made a vector of integer, and then we initialized it to 10, 8, 6, 4, 2. Now we want to sort it. We just literally say sort, and then we pass in 2 arguments. The first one tells the sorting algorithm where the beginning of the vector you want to sort is. And then the second parameter tells the sorting function where the end of the vector that you want to sort is. And in this case, vec.begin gives a pointer pointing to the first element of the vector, and vec.end tells the sorting algorithm where it ends. And finally, after calling this function, the vector would be sorted. And if you print out vec square bracket 4, that would give you 10, which is the last element of the vector, because it's sorted in increasing order. So 10 would be the last one, and this prints out 10. There's more code here, just for your reference. If you want to sort an array, you can do sort array, comma, array plus n, and n is the size of the array. If you want to sort in descending order, you could do sort vec.begin, vec.end. These 2 arguments are the same. And then finally, you need to pass in an extra thing to tell the sort function that, okay, you want to sort in a different order. And in this case, you would pass in greater bracket int, bracket parentheses. Right here, we put int here because we assume that vector is a vector of integers. But if it's a vector of characters, you would have to put character here. If it's a vector of strings, you would have to put string here. And lastly, you can also sort with a custom function. If you have a vector of customized data structures, right? C++ wouldn't know how you want to order these custom data structures. So you would have to tell C++ how to sort them. For today's problems, you won't be using this feature. But in the future, if you need this feature, you can look it up on the documentation, and it's pretty straightforward. And then let's talk about when and why we want to use sorting algorithms in competitive programming. Firstly, when. I summarized 3 points that I think I would use a sorting algorithm when I see a problem. First, when the problem is about sorting, right? When the problem literally says, okay, sort this or sort that, or put these things in a specific order, you would have to sort. And secondly, when the elements of the array have an intrinsic order. When you have an array of integers, and integers can be sorted, right? So when you see this array, you would put sorting on the list of the things you might consider. And then finally, when the current order of the array doesn't matter. Notice that in the earlier implementation I showed you guys, sorting actually sorts in place, which means the original order is no longer preserved. And that's if you want to sort while remembering what the original positions are, you would have to copy the array and then sort one of the copies. Now, why would you sort? First of all, sorting makes it easy to find the nth element in an order. So for example, if you have a vector of integers, and if you want to find the 5th largest element in an unsorted array, you would have to iterate through the entire array to find the 5th largest element. However, if you sort the array beforehand, you can just index to the 5th element in the array, to the 5th last element in the array, and that would be the 5th largest element in the array. And then secondly, what about repeats? Oh, yeah. That's a very good question. When you have duplicates in an array, sorting wouldn't I guess sorting would still help, because sorting, I guess, in terms of runtime, it wouldn't benefit asymptotically, but it's always nice to have a sorted array. And then some algorithms require the array to be sorted before applying the algorithm. For example, binary search, which is an algorithm we're going to talk about next week, requires you to sort the vector before you start using the algorithm. And lastly, but most importantly, sorting is a technique called belongs to a category of techniques called precomputation. Basically, it means to calculate something before you start doing your task, so that it would be easier for you to do your task. It's kind of similar to why you would clean up your desk. It makes some later tasks easier to do. Oops. And then let's take a look at example 1. It's called Satiri. The link is this one, and then the second link is the template, the input-output template for this problem. This problem is very simple. The summary of the problem is here, and it's literally given 3 numbers of a 4-number arithmetic sequence, find the missing one. Let's take a look at the example on the right, and then I'll give you guys 5 minutes to approach this problem. For example, if we get these 3 numbers, and then we were asked to find the 4th number of the arithmetic sequence, it's very easy to see, right? It would be either, okay, actually, let me launch a poll. What do you guys think the missing number is? Okay. Okay. I see most people have already voted. So for this question, actually, for this specific question, you can answer both 30 or 34. But for those people who answer 30, you can give yourself a bonus point, because 30, 31, 32, 33 is a sequence of computer science classes at UCLA. But both are valid answers for this problem. And yeah, if you guys want to work on this problem, I'll give you guys 3 to 5 minutes, and then we'll come back, and then I will talk about the solution to this problem. Okay. So a really simple solution is to use a bunch of if-else conditional branching to find out like what the missing number is. But the problem with this approach is that the numbers are not in order, right? So it's very messy, and it's very time consuming to code. A better solution of this problem would be to sort the array first, and then find out where the missing number is, because we only have 3 numbers. So after sorting the array, for example, in this array, 32, 31, 34, after sorting it, we would get 31, 32, and 34. And now all we need to do is to take the difference between 31 and 32, and then take the difference between 32 and 34. We would find that the first difference is 1, the second difference is 2, which means there's a number missing here. And another possibility is that we would get the two differences would be the same, right? This would be 1, this would be the 1, in which case the third number would be 33. And in this situation, you could just return 31, 32, 33. You could just return 34 or 30. Either subtract the common difference from the first number or add the common difference to the last number. And that's the solution to this problem. And before we go on to the next example problem, I want to talk about something really important, and that is the big O notation and runtime complexity. The big O notation represents the asymptotic upper bound of a function of n, mathematically speaking. This is very abstract, so I'm gonna put it in common terms. It means in computer science, it means how many times do you have to go through the entire set of data using a specific algorithm, ignoring the coefficients and the lower order terms. This might still doesn't make sense to you. So I'm gonna give you some examples. Oh yeah, before we look at the example, one important thing about big O notation is to know that the big O notation is used to indicate the runtime of a program. So how long this program will run comparing to another program, compare it to another program when the input size is very large. Now let's take a look at this first example. We have, in this segment of code, we declare s equals 0. We iterate through an array called array, and then we add each element of array to the variable s. So this segment of code basically calculates the sum of an array of integers. What's the runtime of this segment of code? We would, in terms of the big O notation, we would look at how many operations there are, and then we simplify it afterwards. So let's start from the beginning. The declaration of this variable takes one operation, and then we have a loop. And inside the loop, we have one operation, and that's adding this value to the variable we declared earlier. That's one operation. And then, but it's inside a loop. We run this loop n times. So it would be n times 1 plus 1 operations, which gives us n plus 1. However, when n gets really large, the 1 becomes negligible. So we drop it in the big O notation. We only care about the asymptotic runtime complexity, and that would be O of n. We denote O of n as the runtime complexity of this segment of code. Let's take a look at another example. I'll give you 30 seconds to think about this segment of code before I start talking. Okay. So what does this segment of code, what does this piece of code do? It first declares the variable s. It loops 4 times and then n times. And then inside the nested for loops, it adds each element, it adds an element of the array to the variable we declared earlier. The inner loop looks very familiar to us, right? It is basically the same code as last time. It's adding up all the elements of the array. And then let's take a look at the outer loop. It loops over this inner loop 4 times. However, nothing else is added, or like this A is not referenced inside, which means it's a very simple operation. It basically just does the inner loop 4 times. So let's analyze the runtime complexity of this piece of code. First, we declare a variable. That's one operation. And then we ignore the for loops first. We look at the real operation inside the loops, and that's s plus equals array I. That's one operation. Now, we do this operation n times using the inner loop, and that gives us n times 1. And then we loops over the array 4 times, and that's 4 times n times 1, which gives us 4 times n times 1 plus 1, which is 4n plus 1 total number of operations. However, to use the Bigelow notation to find out the asymptotic runtime, we need to drop the lower order term, which is 1. It becomes 4n. And then after that, we also don't need to worry about the coefficients, because asymptotically, it doesn't make too much of a difference. So, for example, it might seem to you that a piece of code that's 8n, that has a runtime of 8n, is twice as slow as a piece of code with a runtime of 4n. However, when you compare these two runtime to some runtime like n squared or n cubed, they would be on the same level of magnitude, same order of magnitude. So we don't need to worry about the coefficient. And we just say this piece of code has a runtime of O of n. And finally, we have another piece of code segment. And I'm gonna launch a poll, and you guys can see whether or not you can figure out what the runtime complexity of this is. Okay, I see that most people have already voted. I'm gonna tell you guys the answer. It's actually n squared, O of n squared. Some people voted for O of n squared minus n, which is a valiant effort. However, remember that after calculating the runtime, we drop all the lower order terms. In this case, n is still still has a lower order than the n squared, so we drop it. And it has a runtime complexity of O of n squared. What do we need to know? Why do we need to know about this? In competitive programming, knowing the runtime complexity of your algorithm is very important, because if your code is too slow, it doesn't pass. If your code is too slow, it doesn't pass. And in some cases, we can even use the input size the problem tells us to infer what algorithm the problem wants us to use. So assuming that the problem has a 1 second runtime limit, we can use this table to infer what kind of runtime the problem want our algorithm to be. If the input size is smaller than 10, it means your algorithm can be O of n factorial time. If the input size is smaller than 20, then your program can be O of 2 to the power of n. It can be exponential time. And then if the input size is between 100 to 500, it could be telling you that, okay, your program's runtime is probably faster or at least equal to O of n cubed, and so on and so forth. You can refer to this table later on if you want to check it out. Yeah, Jacob brought up a really interesting point, and that is, this is exactly the reason for the names of the levels on the ACM portals: the factorial, exponential, cubic, etc., quadratic, logarithmic, linear, so on and so forth. Now, here are some real examples from contests I did recently. Here, the first one says the first line contains two integers n and n, each are smaller than 10 to the power of 5. If we refer back to the table from the last slide, oh, I actually can't go back. Yeah, 10 to the power of 5. It tells us that our algorithm should be around O of n log n runtime. And then the second input spec tells us the first line of the test case contains a single integer n, which is between 1 and 200. This belongs to the, this tells us that the runtime of this program is probably O of n cubed. And with this information, we can come up with, we can have an informed guess on what the algorithm we should use for this problem. And Rohit is going to talk about example 2 for today.
Okay. So hi, everyone. So we're moving on to the next example, example 2, which is called Basic Programming 2. And here's a link to the problem. And yeah, so I guess I'll give you 5 minutes to look at the problem, but it's basically 5 different subtasks that can be made faster by sorting. So we just want you to use sorting for every problem and see if you can come up with an efficient solution. So I guess I'll pause for like 5-10 minutes, give you guys a chance. Again, just to reiterate, we don't expect you to finish coding, but at least have an idea for each subproblem. Okay, so we're going to look at all the subtasks individually. So starting from the first one, for t is equal to 1, we want to find a pair of numbers x and y such that their sum is 7,777. But in the worst case, that means checking n minus 1 elements for every n elements, which, as according to Tony's previous slides, is O of n squared, which is actually pretty bad because according to the input constraints, n could be as big as 2 million, which means in the worst case, we might have to do 40 billion checks, which is too slow. And your program will most likely TLE. So a hint to make this faster, we're going to use sorting, which is the point of this lecture. So how does sorting help us find a more efficient solution? Okay, so we're going to use something called the two-pointer technique. So suppose you had some unsorted array, and once you sort it, it becomes 1, 2, 4, 6, 7, and 8. And the goal is to find a pair of numbers that sum up to 13. So in the two-pointer technique, I will first tell you, I'll kind of give you a brief look on how it works, and then we'll go through an example to see how, and more importantly, why it works. So suppose, so the idea is you start from the first and the last element in the array, which we refer to as the left and the right pointer respectively. And we basically sum the elements that are under the left and right pointer. And if it's smaller than 13 or smaller than the target, then we move the left pointer. And if it's larger than the target, then we move the right pointer. So let's go through an example to see what this means and why it works. So again, suppose that we wanted a sum of 13, and we have an array that has the following elements. So we start from the leftmost and the rightmost position, which is 1 and 8. We try adding these up, and we see that the sum is 9, which is less than 13. So at this point, what do we know? We tried combining the smallest element with the largest element, and we were still not able to reach the target. Since the array is sorted, we know that 1 cannot be part of the solution because we tried combining 1 with the largest element we have available, and we were still not able to reach 13. So we can safely assume that 1 is in fact not part of the solution, or rather is not part of the pair that adds up to 13. Because we tried it with the largest element, it did not work. So we cannot possibly combine it with any other element, which is smaller than 8, to get 13. So we can safely assume that 1 is not part of the solution, and we can move on to the next largest element, the next smallest element, which is 2. Again, we try combining 2 and 8, which by combining I mean summing up, and we get 10, which is less than 13. Now at this point, we have tried the next smallest element with 8, and we realize that this also is short of 13 by 3, which basically tells us that no matter what element we combine 2 with, we will always be less than 13. So 2 cannot be part of the solution either. So let's try the next one, the next smallest element. And now we try 8 and 14, which again is smaller than 13. Again, at this stage, you should know that combining 4 with any other element will be less than 13, because we tried it with the largest one, it did not work, so it couldn't possibly have worked with any other. Next, we move on to 6. Now at this point, when we combine 6 and 8, the sum is 14, which is actually indeed greater than 13. So at this stage, you can actually safely assume that 8 can no longer be part of the solution. Why is that? Because we tried combining 8 with all the smaller elements, which were 1, 2, and 4, and we turned out that we couldn't reach 13. And now we try combining it with 6, which is the next smallest, and turns out that in fact is greater than 13. So at this stage, you know that 8 cannot be part of the solution because we tried it with all the possible numbers that could have ended up 13, that could have ended up in 13. It did not work. And once we tried with the next one, we realized this couldn't work either. So 8 definitely is not part of the solution. So at this stage, just like we moved the left pointer, in this case, we're going to move the right pointer, which is basically equivalent to saying we want to try the next largest element. So the next largest element is 7. We see that 7 plus 6 is actually 13, and we've reached our target. And at this point, we can quit and return what the problem asks for. So I'm going to give you about 30 seconds to see if you understand this, and feel free to unmute yourself or drop any questions in the chat. I realize it's kind of a lot to think about why it's correct in the first time. I know that I had some problem with this, so if you have any questions, I'll pause for 30 seconds and feel free to drop it in the chat or unmute yourself. Yep, Jacob's absolutely right. So, excuse me, every subtask sort of tells you the power of, or like these problems are used as subtasks in other problems. So you should definitely know how to solve them. And okay, either you guys knew this from before, or I just did a good job explaining. Either way, I guess we can move on. So I guess now that we know how it works, we also need to know when we stop running the algorithm. The obvious one is you found the target, which is great. You can return what the problem asks for. But it's also possible that there exists no such pair that sums up to 7,777. Well, in this case, you will see that the left and right pointer will end up eventually reaching the same element. And at this point, you can quit the program and return that there's no such pair. And for example, suppose the 7 was actually a 6, then at some point we would do 6 plus 6, which is 12. And 12 is less than 13. So we would end up moving the left pointer to the next, which is the right. And over there, the left and right pointer will coincide, and we can end our algorithm claiming that there's no such pair. Okay, great. So now let's look at the next subproblem, which is t is equal to 2, which is determining if the array has any duplicates. And yeah, so I guess an approach 0 is again brute forcing. For every element, you check if you can find a duplicate in the array. And just like before, this is going to be O of n squared, which in the worst case will be too slow and will TLE. So what is approach 1? Well, approach 1 is that uses something known as a hash set. We don't expect you to know this, but if you do, you can use that and get a really efficient solution. But we're going to focus on approach 2, which is sorting the array and then traversing to compare neighbors. Now, what does this mean? Well, look at the example on the right-hand side. If you have an array of numbers and you sort them, then all the duplicates will in fact be consecutive because a 2 is equal to a 2. So a 2 is not greater nor larger than a 2. So they're all going to occur consecutively in the array. For example, suppose the array was 1, 2, 3, 2, 1. Then on sorting, it's going to become 1, 1, 2, 2, 3. So all the duplicates will occur together. And the code is simply checking if the current element is equal to the previous. So in this case, for example, in this code, we first sort the array. And we have a flag that basically tells us whether the array contains a duplicate. And iterating from 1 to the size of the array, we check if the current element is equal to the previous. And if this happens at any point, that means we have a duplicate. For example, in this example, when we start with looking at, sorry, I should have my pointer. We start by looking at 2, and turns out 2 is not equal to 1, so we move on to the next one. Over here, it turns out that this element is actually equal to the previous. So at this point, we say that the array contains a duplicate, and we can return true. Okay. I think I have time to do t is equal to 3 as well. So maybe let's do t is equal to 3, and I'll leave t is equal to 4 and 5 for you to do in your own time and ask us questions during the 1 hour after. Okay. So t is equal to 3. The third subtask was about finding the integer that appears greater than n over 2 times. And this is basically asking you to find the element that is in the majority. So suppose you had the array 5, 5, 3, 5, 2, 5, 2. There are actually 7 elements, and 5 occurs 4 times, 1, 2, 3, and 4. Since 4 is greater than 7 over 2, 5 is in fact our majority element, or the element that we're looking for. And we basically want to find this 5. So again, notice that if the array is sorted, equal integers or duplicates occur together. So once you sort this array, you're going to get 2, 2, 3, and 4 5s. Now at this point, you can simply traverse through the array and look for an element that has a frequency greater than n over 2. And it's easy to do this frequency because these elements occur together. So as soon as you see one, you can start counting. And as soon as you get a count that is greater than n over 2, you know that you've found the majority element. So yeah, so and every time you see a new element, however, for example, suppose we start counting in this sorted array. For example, we see 2, so we increment our count to 1. And then we see 2 again, so we increment our count to 2. But now we see a 3. So at this stage, we've seen a new element. And since 2 was not greater than n over 2, which is n over 2 is 3.5 or 3, then we basically reset our count to 1, which is basically resetting the algorithm looking for a new majority element because 2 did not work. Yeah, and if the count is ever greater than n over 2, then we found our majority element. And I guess a silly question is the majority element unique? And the answer is yes, because if any element exists more than n over 2 times, then you can't have another element that exists more than n over 2 times, because that would mean you have more than n elements. Okay, so here's some sample code. You sort the array. You start with a counter of 1. And this basically essentially means that you've already seen the first element. So you start iterating from the second element, which is I is equal to 1. And you at every point when the previous element is equal to the current element, you increase the count, which is basically looking for duplicates. And if that's not true, then you found a new element and you reset the count to 1. And again, at any point if the count is greater than n over 2, then you've found the desired element and you just break out of the loop because the majority element is unique. So once you found it, you know you found it. You found the unique one. Okay, so we have code for T4 and T5 here, but I think I'm going to leave this for you to do at your own time. The idea is very similar. It uses sorting, and for example, in T is equal to 4, you want to find the middle element, which is what you mean by median. And I'll leave you guys to think about what the middle element in a sorted array means. And for T is equal to 5, again, once you sort things, everything occurs consecutively, so you can just traverse through and check for the given condition, which is looking for elements between 100 and 999. But yeah, if you have any questions about this, please feel free to ask us during once the presentation ends. Okay, well, thank you. I hope this lecture was fun. And yeah, sorting is a really fundamental problem. So I hope you guys got something from this presentation. And if you have any feedback about how the presentation went, or how the example problems were, feel free to fill this out. In fact, we encourage you, even if you have no feedback, just to rate us based on the certain parameters. It's really helpful for us. Okay, so yeah, it's intro CP feedback 4, and I guess we can move on to the contest. So here's a link to the contest, and good luck. Yeah, I think we'll have breakout rooms open really soon, so you guys can ask us any questions you have.